Okay.
Move around? Yeah? Is that okay?
As long as it stays on, it's good.
You can squeeze it. You can squeeze it around your ear. That
Yeah. Okay.
There you go. Okay. And then
Okay.
Testing, testing, testing.
Okay. Okay.
Okay.
Okay.
That's the screens that Bogdan's going to be sharing.
Yeah. Let's see. I won't need it for sure. No, probably not. But see, we'll see.
Testing? Testing, testing, testing. Testing, 1, 2, 3. Can online people hear the sound? We'll begin shortly. Appreciate your patience.
An extra pen. Do you have an extra pen? Can you hear me?
Yeah.
That's okay.
Hello? Can you hear me?
Can you hear me? Okay.
And me too?
So welcome everyone in our special event, and we have a special guests. Also want to welcome everyone online. I think many people join us around the globe, and welcome everyone who come here to listen. Step back. It's okay now? To my left. Okay. Okay. So again, very happy to have you here today in a very special event. And one of our guests flew directly from Dublin, Ireland, Professor Bogdan Staszewski, a dear friend, who is a full professor electric circuits in College University Dublin. We can see, actually you are associated with many universities, I notice, here.
Full-time with UCD, University College
Full-time
Dublin.
with, full-time with UCD. As well, he was for a decade researcher and engineer, designer, or microelectronic and communication systems. And as well, he's very well versed in today's topic, what is quantum mechanics and physics. And it's very good that Bogdan is still maintaining his passion for new discovery in pragmatic applications, the principles what he learned, because with friends from Silicon Valley, they opened the startup Equal One, and actually they built the prototype of quantum computer. So he's fully well prepared for today's discussion, I can say. And what really struck me about Bogdan is willing to really deeply listen and kind of very humble understanding of, he's very well versed in his field, but he's also willing to take any questions and deeply investigate and learn from everyone. I observed this from the decades, have a chance to be with him. So he says, Bogdan, so welcome.
Thank you.
So first, just really want to welcome everyone here to Berkeley Buddhist Monastery for our special event hosted by Dharma Realm Buddhist University. And behind me, on the other side, is Professor Doug Powers at Dharma Realm Buddhist University. He teaches many classes, some that may pertain to today, Abhidharma, a kind of early Buddhist philosophy of mind that develops into Yogachara, which you'll hear some references today, as well as Western philosophy. For being a meditator and Buddhist practitioner for over 50 years, he has led many retreats that bring kind of classical texts from the East, Buddhism and so forth, in dialogue with Western texts. And at one point we even studied Irigare and modern feminism, bringing him her into dialogue with Nagarjuna Bodhisattva, the kind of founder of the middle way philosophy of Buddhism. In addition to that, he's actually at one point ran a refugee center at the 16,000 Buddhas. So his Buddhist kind of practice doesn't just stop on the cushion, but actually comes and manifests in daily life, in, say, serving others. And he's not only a professor at DRBU, but also the vice president of finance and administration. And for many of us who work at DRBU, he carries the vision of the founder, Master Hua, not only in spirit, but actually in daily application. His caring presence, his pragmatic wisdom kind of, you could say, keep many of us going. And as anybody who's worked at a university knows, running a university is not easy. And so we're very happy to have both Professor Bogdan and Professor Doug here today with us to share a very interesting topic. Is consciousness in the universe, or is the universe in consciousness? Quantum physics and Buddhist perspectives. So without further ado, Professor Bogdan will begin first with his presentation. And we have some cards in the middle there, and people are welcome to write questions if you have them. If you're online, you can also write down your questions. At one point after the presentations, we'll take questions, and we'll then review them and then ask them to the professor. And also Doug Powers will ask questions and have a bit of a dialogue. And so it will be definitely a very interesting conversation. We've seen some of these ideas, and they're literally mind-blowing.
So relax, take a deep breath, fasten your seatbelts, and we're going to journey into quantum universal multiverses.
Yeah, okay.
All right. Good afternoon, everyone. So I would like to lead you through this very exciting journey. First of all, I need to make a disclosure. I'm not a quantum physicist. I'm not a theoretical physicist. I'm just an engineer. I spent most of my life in Dallas, Texas, get my bachelor's, undergraduate, and PhD degree, and then went to work for Alcatel in Dallas, and then for TI. And I spent 14 years in Texas Instruments. So you see my card from Texas Instruments. Then in 2009, there was a Lehman Brothers crisis. The sky was falling. The state of California was bankrupt, right? They laid off thousands of people. So I decided, well, let me try my luck somewhere in academia. I've never been in academia. I've never worked even in a research group in company. Always work in a product, and research is kind of considered in big companies a necessary evil. You have to couch it in different terms. You need to say, oh, we need to invent different things because the marketplace requires we can make more business inventing. You never use the term research in a big company. So I wanted to use the term research. So I went to TU Delft in the Netherlands, one of the highest ranked schools is in my area of microelectronics. And then about 9 years ago, I went to Dublin, University College Dublin. And there I started a company, Equal One. So I'm going to show you the path that led me as a simple engineer to get into a company that is basically trying to build the first world's practical quantum computer. So the journey started in '95. I joined Texas Instruments, and TI was a fantastic company. It was one of the most pioneering companies. The innovation was at the grassroots level, unlike IBM, where basically all the decisions were top down. In TI, they told me our motto is don't ask for permission, ask for forgiveness. Just try to do something without telling management, and if it works, that's fine. So integrated circuits got invented by Jack Kilby. He got Nobel Prize. He was the second engineer that actually got Nobel Prize in physics. And only his boss knew about this, nobody else that he was working. Then it led to creation of calculators, speak and spells, and then TI popularized DSP because this was necessary for oil exploration. They were getting so much data, digital light processor, and my contribution is digital radio processor. So the spirit of innovation of Jack Kilby was there very strong. He invented IC chip in 1958, only his boss knew, right? So he patented before Intel. So I'm going to speak a little bit about TI, but I also give an honor to Intel, something from California. So that was his first multivibrator. Then he went on and applied the integrated circuits technology for the world's first calculator. So this calculator would cost a price of a small car, basically. But it was fantastic sell with accountants because previously they would use abacus. It's a great history, great work with microelectronics. I studied vacuum tubes when I was a teenager. I never dealt with vacuum tubes, just studied how they work. Then I went for transistors, and then I started dealing with integrated circuits. And the scales of these electronic devices, 1-bit electronic device, so one function, has been going down tremendously over the number of decades, right? To the point where we are somewhere over here. This is a pretty obsolete Intel's processor, 22 nanometer, is considered almost ancient. The bacteria size is something around 1 micrometer. Virus is about 100 nanometers. So these dimensions are well below the size, wavelength of light and whatever organisms that we have. And we are getting to the point where we are basically just touching upon single atoms. Just individual atoms, and this is what allowed us to exploit this for quantum computing. So just to give an honor for Intel, this is their view of the Moore's law of scaling, which basically every 2 years, the number of transistors double, the power consumption gets almost 1/2, and this has been going on regularly for decades, basically. There is no stopping. This is like a economical law that has to happen. And In 1971, 4004 Intel processor had only few transistors. Then 8080, 8086, that's a very famous one because that's the base of current computing. And it's been keep going on. The processing power in terms of millions of operations per second and transistors is just humongous. So nowadays, Intel puts 100 billion transistors on a single die. So in TI, in 99, I moved from Rechannel Group for magnetic recording, disk drives, to DRP Group, digital radio processor. I basically started with a few of my colleagues. We had fun. Our VP was Ming Chang. He was from Taiwan, and he gave us lots of opportunities. For what? We wanted to make the cell phones as cheap as possible. So we were working with Nokia. Nokia's motto was cellular chips, cellular communication to the masses, and the entire cell phone, which was the size of the brick. Remember these 007 movies? Very sexy phone was the size of a brick. We basically put it in the size of a chip, microchip, very small, right? And it had everything, all the functions required to transmit and receive data was there. This is a chip micrograph. We've been selling millions of these units per day. Million per day, so it's incredibly huge volume, and for this reason, everybody now in Africa, for example, can afford a phone, and they can use phone for doing the local businesses. So while putting into production these high volume radio chips, on the spare side, we had lots of time, and I was working very inquisitive people. Jean Wei mentioned that I have kind of tendency of getting always into trouble, like look deeper than necessary and get into trouble. So we hired one PhD from UC Berkeley. He came for the summer, and we implemented the single electron device. So what does it do? You have a small capacitor. See, this is the equation for if you are studying electrical engineering, you know that. The charge divided by capacitance. This is a single electron charge, right, which is fixed, divided by a small capacitance. If this capacitance is tiny, the voltage difference is quite large. So you can detect it very easily. And we wanted to build a quantum processor on a cellular phone. So we implemented this. This is a typical layout. We have a polysilicon, we have a diffusion area, active area, and there is a little bit of overlap, and that overlap determines the capacitance between them. And if the capacitance is small enough, then the energy that we'll get is greater than thermal energy. Right? So you have vibrations, matter vibrates, you have molecules, electrons, protons, they vibrate because of heat, right? And they always vibrate and they create some noise, and that noise is bad for quantum computation. So we would like to slow down the vibrations to such a low rate that they will not affect quantum operation. And that temperature is near absolute zero. Minus 273 degrees Celsius below zero. I don't know Fahrenheit, but it's something like 500. So we studied lots of papers. One of the models was Likarev model, where we have this tunneling, we increase the voltage, and boom, here a single electron can go through. So using the traditional process technology, you can just manipulate single electrons, and this is at zero temperature. 0 Kelvin temperature. Here we can use it at room temperature. So we fabricated these chips. This is a tunneling electron microscopy. You can see where we can build these structures with very small capacitance. But the year was 2008 and things were not going fine, so we decided to leave Texas Instruments, and then I went to TU Delft and University College Dublin, and then when I reconnect in 2017 with my former colleagues who were physicists, they had PhD in physics, they were designing fabrication processes, we said, oh, guess what? Now process technology is fast enough. We can build these single electron devices quite reliably, and we can use it for processing the data. And between 2015 to 2020, which is 2 CMOS nodes, very short period of time, the amount of data has grown 18,000 times. It's 18,000 times to 44 zettabytes. It's impossible to process this data. So you need quantum computing to process the data, right? 2 days ago, I visited Stanford National Accelerator Laboratory, presented them with similar things. They're very excited. They use quantum computing mainly for sensing. They have a project on dark energy, and they need to build thousands, tens of thousands of these detectors in order to figure out what constitute dark energy. And of course, if they succeed, there will be Nobel Prize, right? So somebody will get this. So this is what drives in Slack. Also, quantum computing will be good for climate modeling, or also figuring out, finding the cure for AIDS or cancer. You can plug in all the parameters into quantum computer, and after a few minutes, it will spit out the solution, the material to solve any drug problem or a cancer problem that you might have quite easily. Quantum computing could also be used for very simple classical algorithms like traveling salesman problem. So whoever studies computer science knows this problem, right? It's a very simple problem. You have a traveling salesman that goes to these cities, and there are 5 cities, and this is the distance between the cities. So the task is to minimize the number of miles traveled between these cities, right? So you need to find out. And the complexity of this, the number of solutions, is n factorial divided by 2. So for a small number, you can guess it very easily, right? For a medium number, you can just plug it to a regular computer and it will tell you very quickly. But if you have to find 50 cities, if there are 50 cities like that, the number of solutions that the computer has to go through is 3 times 10 to the power of 62. Do you really realize how big number it is? How many atoms are in this galaxy? 2 to the power of 66. So almost this is the number of atoms in this galaxy. You know, so no power on Earth. I don't care how many computers you take, classical computers, they will never be able to solve in billions of years for a very simple problem, right? So what even speaking about finding disease for a cure for diseases or climate modeling. So we know the equations. I mean, the algorithms is very well known, is that we don't have computing power basically to solve it. So quantum computers are necessary for this. And also, some people think, some scientists think our brain is nothing but one big quantum computer. Why? Because it consumes 20 watts of power, right? And it has trillions of these neurons, and somebody calculated that if you want to implement this using the most advanced CMOS technology, chips, you can still do that. You can have all these neurons, but the power consumption of this required will be that of a nuclear plant, basically. So nuclear plant on one side versus 20 watt. 20 watt is a dim light, basically, dim bulb. So human brain is able to do that, believed to be because of quantum computation. So we all know that quantum computation is very important, right? It's going to change the society and everything, the way we work, we live, much more than invention of integrated circuits. And look at Silicon Valley, right? I mean, it's based on integrated circuit and how much change has been here because of IC business. But it's not easy, right? Qubits are very fragile because they are subatomic particles. They are not even atomic, they are subatomic particles. So they have to be manipulated. They have to be read out when the quantum experiment is being done. And even a single mistake can just destroy the quantum state. So we need to use qubit errors, quantum error correction in order to help this operate correctly. So when you look at today's quantum computers, they exist, but they are kind of toys. This is one of the examples, Josephson junctions. It's not microelectronics. It's based on Josephson junctions, Cooper pairs, where you have basically 2 electrons traveling. And the problem is with this is that it works, but it cannot be scaled up. So the best thing quantum computers currently can do, they do work, no problem. The best thing they can do is to show 21 is equal to 7 times 3. factorization of the two prime numbers. 7 is a prime number, right? 3 is a prime number. They cannot go higher. And that with a confidence of 90%. So people spent tens of millions of dollars just to find out that 21 is equal to 7 times 3, basically. That's the best thing quantum computer can do. It costs a lot of money because most of the hardware needs to go to cool it down to absolute temperature, 20 millikelvin. Right above the absolute zero, where everything stops. Basically, there are no vibrations, so it's extremely expensive, and you have lots of cabling and so on. But the quantum processor by itself is quite small. IBM has been pioneering, so the reason I show IBM is because we collaborate with IBM. We are part of IBM Q network. They have a big presence in Ireland, so do most microelectronics, US microelectronics companies. And when you look at the inside, so this is a quantum computer, lots of machinery to measure, but the actual refrigerator is here inside. When you open it up, you will see it will have different stages, right? So one stage, it's 70 Kelvin, then 20 Kelvin, then 4 Kelvin, going all down to millikelvin temperature, where you put your Josephson junctions there. And it takes weeks to reach that temperature, and it can only dissipate a few microwatts of power. So it's a very difficult, very expensive, very difficult to build quantum computers. My colleague from TU Delft, Van de Sippen, he was invited to this most prestigious conference in my field, ISSCC. He gave a keynote, and this is one of the slides that he presented. Basically, this is time, evolution of time, and number of qubits, right? So, there is a exponential increase in the number of qubits. So every few years, we are going to add a few qubits, basically, right? And how many qubits do you need? If you want to calculate 21 is equal 7 times 3, the factorization of the two prime numbers, you need to be somewhere here, right? If you want to predict weather, find cure for AIDS or COVID, then you need to be here. Over here, you can solve any problem whatsoever, right? So we're kind of saying that if we get here, one of the first tests that we will do is to break into the Swiss banking system, because we're able to crack the code. That will be simple tests, right? If we can pass it, it means our computer is useful, right? Usefulness. Because, you know, it's difficult to get funding, government funding, right? So one way to get funding is to break into the Swiss bank account. But to get there, it will take a long time. So he stated that by the time he retires, he's hopeless. And maybe even his kids will be hopeless to get this. So he proposed this, right? But this is exponent over exponent, right? Which never has happened before. But engineers are a very inventive bunch, and many companies are working on this. IBM, Google in Silicon Valley, IBM in New York, and Rigetti and D-Wave are working on this using superconducting approach. There are many approaches, right? Superconducting, I showed you, is probably the most classical one, the first one. There is also ion trap, very good qualities. The ions are laser cooled to nanokelvin temperatures, basically, but they are not really scalable. They are very good for experiments, physics experiments, but not scalable. We also have photonics based on photons, right? Polarization, vertical or horizontal. And some people are doing semiconductor-based qubits. So this is my company that I started is one of them, but we also have some competition, which I hear breathing at my neck. The way quantum computers are currently done is basically you have this quantum processor, Josephson junction, superconducting. There is no power dissipation, nothing. You cannot dissipate, run any current over here. And the operation is done in this chip. It's not CMOS technology, so it's a very boutique kind of process. And you have some control signals, and then you have microwave pulses. So, and then you run quantum experiments, and you get very weak data, so you amplify it. And all this equipment is at room temperature, basically. So you have 15 millikelvin on the left side and 300 Kelvin room temperature on the right side. And when you look at these IBM quantum computers, you see lots of wires. Each qubit requires 10 to 15 wires, right? So if you need to go go to million qubits, as here, I cannot envision you putting millions of these wires. And they have to be very precise. So there are some companies, some students in TU Delft, they started a company, they are selling these wires. And each little wire costs like $3,000, basically. So, so they are the only people making money, right? People that are making, companies that are making shovels and picks, right? They are making money. Everybody else, like Googles, IBMs of this world, they are just spending the money, right? Similar thing happened in California, right? With a gold rush. So that's a good business. So in TU Delft, what we propose that we will put electronics, the conventional electronics, at 4 Kelvin temperature. So yeah, we have some controller, monitor, keyboard at room temperature, 300 Kelvin, right? We have chips operating at 20 millikelvin doing the processing, but the drivers is operating at 4 Kelvin. And it means that the driver basically will be locating somewhere here, the chip, and there will be a few wires going down to 20 millikelvin. But when I got back with my colleagues, we decided that that was the wrong approach, because we wanted to get 2 million qubits and we need to leapfrog, and everything has to be on the same chip. So we proposed that the qubits, the whole quantum processor, will be integrated on the same die. So this is a single chip here. This is done from Global Foundries, right? 3 by 3 millimeter, we actually fabricated this chip, and it's very small. And because everything is on this chip, the qubits can operate at 4 Kelvin, and we can put it in this commercial cryocooler at 4 Kelvin, right? You can buy it for $60,000. You can buy from Montana Instruments. And this looks something like this. They provide you with electrical connection, and it looks like a coffee maker, basically, right? So put it on your table, and sample runs at 4 Kelvin. You can run operation, and your colleagues thinks you are just a coffee addict. And the transistors, we can do that because the transistors are becoming very small. They are becoming tiny, right? And you can actually put, this is a single transistor. What we have is the gate length of 22 nanometers, right? That's the process, 22 nanometer. So it's extremely small, right? 22 billionth of a meter, very small. And this size is about 50 nanometers. So it's a small size that we can effectively put a single electron, and then we can manipulate this electron for the purpose of quantum computing operation. So if you are into IC chips, you recognize that this is a transistor. So we are using process as is, right? It meets all the requirements. We are just using these transistors in a different way, right? We are controlling individual gates, individual electrons. So this is a potential, the voltage energy potential diagram, right? So we have one quantum dot over here, the well, which is like a source drain normally. If you use it as a transistor, we have another one. And then when we electron is not a cannonball. It's not a ball, right? It's a wave function, basically. So this wave function is shown over here. Because of the energy potential here, the wave functions cannot go through because the energy is too much. So it has to decay to 0, and the most energy is right in the middle. But if we lower the barrier, then this wave function can move to the neighboring point, from here to here, basically. And we can put a detector, and remember the capacitance is very small, so I can use very simple detector to find out, do I have an electron there or not? Very simple, that consumes very little power. And we have the state 0 or 1. So yeah, so we built basically the whole structure like this. So we inject the electron here into one of these wells. Then we lower the barrier, and there is a Rabi oscillation of this wave function between the two. Then we raise the barrier, and the electron is over here. But if we raise the barrier at this point, then half of the electron will be in this quantum dot, half in this quantum dot. And if I take this to the end of galaxy, there will be still one electron, but in both places at the same time, basically. So it's possible. It's called superposition. Quantum physics does that, and it's been demonstrated many, many times. For quantum computing, you need to have entanglement. So basically, you have similar structure like this, but you have another one at the bottom over here. So we inject electron here, we lower the barrier, there is a tunneling. We raise the barrier, so half of the electron is here, half of the electron is here, and then we inject the electron on the top side, right? And then lower the barrier, and now there is a interaction of the two wave functions, right? And that gives us two-qubit quantum gate, so we can realize various quantum gates. So with these ideas, we started a company in California, in Silicon Valley, in 2017. It was registered in California. We went to Google, Facebook, and we showed them this, looks fine, but they were kind of laughing. You guys are crazy. Who needs quantum computing? You are too early. So we didn't have much luck with getting funding from Silicon Valley because we are simply too early. So I convinced them, hey, let's try in Ireland. The government is kind of more conservative, and they are always looking of getting these American companies, right? I mean, Apple used to pay how much? 0.01% taxes, right? So they know how to get American companies to Ireland, so they give them money, and we basically moved the headquarters from Silicon Valley to Ireland, but the people, the main key people, they still stay. So they work there. And we get money from IBM, Q, and Atlantic Bridge on Sand Hill Road. I visited 2 days ago. They are still there. So this is a chip, the micrograph of the chip that we are building, that we have built. So we have sea of electrons over here. We lower the barrier. The electron gets here into this position. And this is a top-level view of something which I showed you before, of this one here, right? So we have gates, and then we have this the active areas over here. And then we manipulate the electrons. We inject the electron here, they get here, and then there is an interaction. They get entangled, right? So they have the same property, and we can do quantum computation with that. So the chip is very small, 3 by 3 nanometer. This is the layout. This is a chip micrograph. The separation between these balls is 250 micrometers, so we can put lots of them. So effectively, we can basically build millions of these. And then we put on a cryocooler head, 4 Kelvin. We enclose it, and this looks like this. So we have all the electronics to drive it, to process on the same silicon chip. And for production, we are planning to put it in production, if we are lucky this year. This is the quantum computer, basically, size of a Dell tower, basically, right? It consumes something like 1 kilowatt of power. It has a good heat extraction capability, and if it works, then it can hopefully change the microelectronics and computer science as we know it. Okay, so I gave you this presentation because this is Silicon Valley, right? So one way of connect with Silicon Valley people is to talk about silicon, right? So this is the silicon. So now I step back and talk about quantum, right? So what is quantum mechanics? Basically, it was observed by Schrodinger that every particle is a wave, right? Which basically extends for infinity, right? And it is characterized by the wave function, psi. And this is Schrodinger equation. So one thing, and the absolute value squared is shown over here because it also has phase. Schrodinger and the scientists, after this equation was formulated, didn't know how to explain it. So this is a wave functions, but they didn't know how to interpret it. And then it was reinterpreted by Born as the probability. So this is the equation, and notice that this psi wave function evolves based on energy. You put energy, it evolves, and versus space, it has a special spatial space-like characteristic and evolves over time. There is no randomness here. So people that tell you that quantum physics is random, it's not true, right? There is no randomness here. Everything is deterministic. 100% deterministic. There is absolutely no randomness. So Born was the one who say, oh, psi modulus square is a probability of finding a particle in that place, right? But if I have an electron, that wave function can extend to infinity through the whole galaxy, right? So that electron can be in the whole galaxy, basically. If I'm looking at it, it's just observing it, it happens to be here with this probability, or here with this probability, or here with this probability. So basically, this is what it means. The world quantum at the microscopic level is different. For example, tunneling. If I have a wall, strong wall, the car cannot go through wall, but a particle can perfectly go through wall, because particle is not a cannonball, right? It's not a ball. It's a wave function. So wave function can go through the wall, no problem at all, right? And it happens quite often. For example, if you turn on your computer, 30% of the energy lost to the battery, through the battery, is because of this tunneling. You have particles which are basically tunneling through these very small structures of the transistor. That's 30%. So you pay penalty, you suffer from this, because batteries don't last very long because of this tunneling. So this is real. Quantization. In a classical system, we can have any speed at all. So we can have slower, faster, whatever. In a quantum system, we can have only limited amount of speed, right? So the speed is the same, either slow or very fast. So we are limited. Superposition means that a property of a particle, like spin or location, can be in both places at the same time. Remember, I showed you this when we have an electron, we split into two parts of the wave function. I can take another part of the wave function to the end of the galaxy, and that will be still the same electron, right? In two places at the same time, right? So spin can also be in two places at the same time. Whereas in the real world, our world, the cat can be this location or this location, right? There is no disagreement. Entanglement means if I take particles, entangle them, and take one of them to the end of the universe, there will be entangles. If I look at this particle, the other particle will be affected instantaneously, basically. There is no time lag at all. So they will be still entangled, and nobody can explain why. Einstein never agreed to this, and some people give you an explanation, because we don't know what the state is. So this is what Einstein was about. He said that there are some hidden variables in these particles, but the experiment in TU Delft basically put the end to this, that there are no hidden variables. Indeed, they are truly random, right? So you cannot use this example some people try to do. So for quantum computer, we basically, it's an extension of classical bits of information. You have state 1 and state 0. In qubit, you also have two states, but you have superposition, basically. So according to this equation, state 0, state 1 with a certain probability. So it's not that you don't know what that probability is, it's just they are both at the same time, basically. Right? Until you perform measurement. When you perform measurement, it collapses to either spin up and spin down, but until the measurement, you don't know what that value is going to be. And for quantum computing, we use so-called block sphere, right? This is a classical state 1, North Pole, South Pole, classical state 0. But the superposition, if we are in the equator, it means we are both state 1 and state 0 with 50% probability, right? And we can change the probabilities as well. A regular computer, you don't have it. So this is the reason that quantum computers, because of superposition and entanglement, they are much faster. They can do things in parallel at exponential speed. So they can solve problems which regular computers cannot solve for billions of years, right? Because they do this thing in parallel. Okay, and as I mentioned, in 2017, we started projects, and we moved to Dublin because we couldn't find companies willing to sponsor it. And I had one Iranian student, and he said, can I work on this quantum computing? We looked at the export license control book, right? The US government publishes. There was nothing, no mention about quantum computer. It means they thought it's a fairy tale. Quantum computer fairy tale. So can we put Iranian student? No problem. It's a fairy tale. It will never work. And then the breaking point, the Sputnik moment came when the Chinese actually showed the entanglement of two photons through the satellite. And that was the Sputnik moment, when the Americans realized that they are far behind, basically, and the Chinese are leading this. So this is all changed, basically, from that moment. This satellite experiment basically changed. So quantum communication between the two cities in China basically just opened up eyes for everybody. So how this happened? Well, until 19th century, Newton's interpretation of light as particles that are coming in, impinging in our retina, was ruling the explanation. But Young did this experiment, a double slit experiment in 1801. Basically, you have a light parallel from a long distance, right? And then you have two slits. You have a screen, right? And then you have two holes in this. And when the light gets there, it's like water, right? It starts ripples, basically, creates waves. So there is a wave front over here, there is a wave from this, and there is an interference pattern because the two waves interfere with each other. So he was able, and then when you put the screen, observation screen over here, then you will see this kind of pattern, right? And this is clearly something that you see observing water, basically, right? So it was very clear that the light are not corpuscle, they are not particles, they are waves. So he said Newton was wrong. And why this happens? Well, because if light has a wavelength, right? So if you have a number of wavelengths here by pi, by lambda, then basically lambda divided by 2, then they destruct. This is called constructive destruction. And when they have the same phase, they add up. So when you measure it, you get something like this, right, in the real. And if you do it many, many times, you get observation something like this to basically show you the wave function. So you can show this also here if you have some, this is a cartoon, obviously. If you have bullets, right, you go through one, basically we are putting through two slits. You fire bullets here, you obtain this kind of distribution, right? Because the bullet, when it goes right through, it has a higher probability. When it gets close to the edge, it can get reflected sometimes, right? So you get less probability. You get through this slit, then you shoot the bullet through the slit, you get something like this, and the total is something like that. If you have water waves, right, the water goes through this, it produces this distribution. We open up this slot, it produces this distribution, right? So when there is only one slot, you get this, which is very similar to just a particle. But if you have two slots, then you're going to get this interference pattern. So that's why it's called double slit experiment, right? You get interference of these two waves. Now, interesting thing happens with electrons. When you send electrons, individual electrons, and the size is small, if you close this thing up, you get something like this, which is normal. If you open this one, close this, you get something like this. But when you fire individual electrons through both of them, you get something like this. What you send one electron, right? I mean, many electrons are shown in order to get this pattern, but individually at a time you send just one electron and you obtain something like this. So it means that electrons are waves basically. Right? They are not just matters, they are electrons, they are waves when they are going through. But when you observe, for example, the electron coming through this, then they are no longer the waves. So the observation of the electron traveling through this, so a single electron creates this wave because it goes at the same time through this slit and through this slit. But when you observe one of these slits, then they are no longer waves. They are, no longer particles, they are waves. So Wheeler, he was a very famous professor in Princeton of physics. He came up with this experiment. Basically, you have a source of single electrons, you send them, and there is a beam splitter where half of the electrons go here. Statistically, half of them go through, half of them get reflected, right? And here there are mirrors. So you observe 50% of the electrons 50% of the time at the top detector, and if you put another detector over here 50% of the time, right? It means that the electrons travel of particles. They travel here, either has 50% of probability of reflecting or going through and comes back. So they are particles. They are not waves, basically. They are particles. But if you put another beam splitter over here and make the dimensions correct, then you don't observe anything coming here. You only observe electrons coming here, simply because when you add up all these wavelengths, there is a destruction for this path. So it means that the electrons coming here are waves. They are adding as waves. So now Wheeler had a question. How does the electron, when you are sending the photon or electron, how does this photon know that you have a beam splitter over here? There is no way. And many experiments actually were done where this beam splitter will be randomly placed when the electron started moving, and the results was the same, basically, right? So somehow this photon knows whether there is at the end of the journey, there is a beam or not. So he extended this experiment to galactic sizes. Basically, in a far distance galaxy, there is a quasar, right, which produces this super powerful burst of photons. And the photon goes to Earth, but there is a galaxy in between, right? And the galaxy, according to Einstein's general theory of relativity, is a lens. Is like a lens. So it reflects the electrons with 50% probability here and through this path. And on Earth, if you look at this path, as if the quasar was here, you observe it with 50% probability, and when you put your telescope here, you observe it as here. So they all behave as particles. But if you, on Earth, if you put the same beam splitter as you do it here, then only one direction will be possible. So you see, this was a very shocking discovery. So how does the photon 1 billion years ago, emitted from another galaxy, travels all the way? How does it know that it's going to be observed after billions of years? And it took on the wave or particle nature, right? The electron is being sent as wave or particle, right? Billions of years ago. How does it know which nature to take? So this was stunning. So he basically says, past has no existence except as recorded in the present. So it doesn't matter what happened billions of years ago. It happens when you measure it now, you go back into past and you interpret what happened in the past, right? So past does not exist. He said universe does not exist out there independent of all acts of observation. So you need to observe it, because if you don't observe this, you don't know whether the photon had a nature of wave or particle. So he's just one camp he's a very famous physicist, just one camp. Most physicists, I would say, they belong to so-called Copenhagen interpretation of quantum mechanics, which was developed by Niels Bohr, which was Danish. And it included this prestigious club like Werner Heisenberg and Max Born. So Born was the one who gave a notion to psi squared, wave function squared, is the probability of finding a photon particle there. They also use principle of complementarity, meaning the objective, the properties cannot be measured simultaneously. So for example, position and momentum cannot be measured simultaneously, right? If you put emphasis on one, you destroy the other accuracy, and so on. Act observing and measuring is irreversible, right? You have a wave function, you observe it, it collapses, basically. So it was nice, it was deterministic, there was no randomness in this. You measure it, you introduce randomness, and you basically destroy the whole thing. And no truth can be attributed to an object except according to the results of this measurement, right? So that brings a question, what is the reality? Right? If you cannot put any truth into the objects. At quantum description are objective, meaning that they are independent from the physicist's personal beliefs, right? So subjective perception doesn't matter. And they could not explain lots of phenomena. So basically they came up with the motto, shut up and calculate, right? Basically, don't waste your time and energy trying to explain why it works. It does work. Schrodinger equation work 100%. So far, it hasn't been disproven. You can use it to find out all possible things. If you have enough computational power, you can predict lots of things. It does work, but simply they don't know how to interpret. And they don't want to interpret, right? They have lots of things to do, like building atomic bomb, quantum computer, and so on, without even understanding why it works. Einstein was not very happy. He never joined this club. He didn't want to have anything to do with this. He had his own theories of hidden variables, which were kind of proven incorrect, right? So don't think Einstein was always right. He made many mistakes. Theo Delft actually did the final experiment with Bell inequality to prove that he was not correct. Schrodinger also was dissatisfied. He never joined this club. He has his own explanation. But here I would like to summarize the Schrodinger equation, right? So we have a psi wave function, right? We have energy acting on this psi function, right? And there is a revolution of time. So it's not random. And time can go forward and backwards. So this equation doesn't say like all physics, fundamental physics equation. The time can go forward and backwards, right? Only when you put thermodynamics, like statistical physics, not the fundamental physics, but statistical physics, right? Then there is the entropy, and the time only has one direction. But fundamentally, there is no preferred direction. So time can go both forward and backward. And if you want to stun theoretical physicists, ask him or her question, what is wave function? That's the best, or what is the observer? That's the best way to stun them. So here you have a nice wave function, as I have shown. When you observe it, you get something like this, right? So you have a source of photons or electrons go through these double split. It creates these wave-like properties, right? But if you observe one of them, then it turns to this, basically, that the wave function basically collapses. Nobody knows what the wave function collapses. Schrodinger equation is silent about this wave function collapse. Nobody even knows how to describe this mathematically. There is no wave function collapse here, right? So this is a big problem confounding physicists. So, Einstein was also kind of hesitant. One time he said, if I don't look at the moon probably doesn't exist, right? Meaning that before you observe, everything is a wave function. So this is the whole universe. This is the whole world, right? Exists before we observe it. When we observe it with our consciousness, we see this. But if we don't observe it, we see this bunch of wave functions, right? Schrodinger was unhappy with the Copenhagen interpretation, so he devised this so-called Schrodinger cat, Gedanken experiment, thought experiment, where basically cat would be killed. So he was compassionate, he didn't want to kill the cat, so that was a thought experiment. So basically you have a radioactive material which randomly just sends an atom, decays, right? And there is a detector, like Geiger cell detector, right? And when that radioactive event happens, then the hammer is released, break the poison, and the cat is dead, right? So that was a thought experiment. So until we observe this decay, radioactive decay, we don't know if it happened or not, right? So it's in the state of superposition. So because this leads to hammer, leads to poison and the cat, until we open up, so if the cat is a closed system, until we observe the cat, we don't know if the cat is alive or dead. The cat is basically in the state of superposition, is both dead and alive, basically. So that's the only explanation. Obviously, it defies logic, right? How can cat be dead and alive, right? So it defies logic. And up to this moment, physicists don't know how to explain it, right? This is a big issue with Copenhagen interpretation of quantum mechanics. Now we had Hugh Everett, very famous physicist, who got his PhD in explaining this apparent issue with Copenhagen interpretation. He said there is no wave function collapse, basically. Every time something like this is supposed to happen, the cat is supposed to be dead or alive, or we observe the wave function collapse or not, the universe splits into two, basically, right? So every time something happens, the universe splits into two. So it means that the observer is in the state of superposition, basically. So he defended his thesis in 1957. He became a very famous professor, and up to this moment, nobody could find a flaw in his thesis, basically. So he started lots of explanations. So according to him, there is no classical realm. It's all an illusion, right? Everything in quantum, including the observer, is an illusion, right? And the wave function never collapses, basically. The universe just splits. So if something happens, there is a scene from real life. If there is a decision, right? Obviously, she makes the decision, right? So if there is one decision, this happens, right? If the decision is different, then this happens. So the world splits into two, basically, right? Something like shown over here with a cat. Then there is another decision, right? They might have a kid or not kid, right? They can still be together, right? Or he's alone here, and maybe he finds somebody else, right? So every time something like this happens, there is a split of the universe. So the reason I mentioned this, but to me, the Buddha never mentioned about parallel universes, right? They are very famous in sci-fi movies, but Buddha never mentioned parallel universes. So we are still thinking what it is. When we are discussing why quantum computers are so powerful, the leading explanation in my company, which I started by the physicists, so we have theoretical physicists in California, in Fremont, and our favorite explanation is parallel universes. And this was actually propagated to explain how quantum computing works by David Deutsch, who is a very famous physicist, basically. He's like the father of modern quantum computing. So the reason quantum computer works is because there are decisions, right? We prepare the qubits and everything. We let quantum experiments run, and the world splits into parallel universes. And before they get too far away, we get the results from the different universes and feed into our quantum computer. That's why they are so powerful. We can run billions, gazillion times faster than regular computers, which don't harness the power from parallel universes. So that's our explanation, right? Is it true? Well, I mean, nobody knows. We haven't observed parallel universes, but that's the most logical explanation, which basically the father of quantum mechanics has come up, and he's propagating it. So what does it mean for Buddhism? Until the first quantum revolution, right, until Schrodinger and Heisenberg, there was a Newtonian mechanics, which basically was Hamiltonian. You have different particles, masses, momentum, and if you know the momentum of every particle in the universe and all the energies, you can predict the future going to infinity, basically, because everything was predictable, basically. There is no randomness. There could be chaotic system operation. If you have many bodies, you don't know, but you don't know simply because you don't have enough computational power. But it's all 100% predictable according to Newtonian mechanics. And Newtonian mechanics was until the first quantum revolution. So for example, it affected such great thinkers like Schopenhauer. So he said, I do not believe in free will, because if everything could be calculated mechanically, right, including vibration in your brain, there is no free will. Everything is basically determined, right? But the first quantum revolution has introduced randomness, and that randomness gives gives, it's a fundamental, it's at the very core of quantum mechanics, there is a randomness, right? You observe the wave function. I call it first quantum revolution because it's kind of considered now a bit incomplete, obsolete. That's a Copenhagen interpretation, right? But for the first time, there is a randomness, and there is a possibility for free will. So this opens up a path for possible reconciling religion, spirituality with science. Okay, there is also a very interesting discussion about Atman, self, early Buddhism. So basically in Buddhism, according to early Buddhism, the self is just a stream of independent arising events. We call them skandhas or heaps, right? But there is no permanent reality, permanent entity into this. There is no Atman or soul, as we call it in the West, soul. In India, when it was developed, they call it Atman. There are two different views of self, right? There is a substance self and there is a process self. So substance self will be like Atman, Indian Atman, or soul. There is a soul somewhere in us, right? And that soul is indestructible, right? It's there, survive. In India, it goes from one body to another. There is a reincarnation and so on. In Christianity, the soul after the death gets released and goes to heaven or hell, whatever, right? But there is also a separate, different interpretation of self, which is a process self. That self is just a process, like you're running a program, computer program, and the running of the computer program is that process. There is no substance to it, right? So there is a dependency on the previous, whatever happened previously. And Buddha many times said, I should diligently practice to reach Nibbana, right? If he doesn't believe in the substance cells, why did he use I here? Right? So he used the term Atman to mean for you should practice yourself, you should exert yourself, right? Because he accepted the notion of self as a process, not as a substance, right? And when you look at the Western religion, they will not agree, obviously. Christianity doesn't say self is a process, self is a substance, but the modern science, biologists, psychologists, psychiatrists, they certainly would agree that the self is just a process, right? So there is lots of agreement, but there is a disagreement, right? The difference between Buddhism and science is at the beginning and at the end. Now, so there are different thoughts throughout Buddhist philosophy. So the first turning wheel, which is Pali Buddhism, early Buddhism, is Atman is just an illusion, but dharmas exist, right? So there is a saying, you cannot enter the river twice, because the river is always like river of your self, always evolving. So you're never the same because the waters basically are always new. The river might be the same. The second wheel, which is Madhyamaka, Mahayana Buddhism, basically say, well, you cannot enter the river even once because it doesn't exist, right? There is Atman and self, they are illusions, right? So you cannot enter that river even once. So that is a innovation into the Buddhist philosophy. The third turning of the wheel, Yogachara, basically doesn't really disagree with the second one. It's just say it went too far. It basically says people became nihilists, some of them. So they basically says you and the river are the same. Right, you cannot enter the river because you and the river are the same, right? And Yogachara basically at the core says objects do not exist outside of consciousness. So many people, early Western philosophers, they read the first part, objects do not exist, but they miss the second part, outside of consciousness. So they say, oh, objects don't exist, so everything is idealism. Right? We only live in a simulation. Like Elon Musk said, he thinks we all live in a simulation, basically, based on his observations. So he's convinced we live in a simulation, but simulation of what? Inside the computer? He didn't say that. So objects don't exist outside of consciousness, and this is the important thing. So it means that it also solves the mind-body problem of the Cartesian model, right? Okay, so this is the Western model. So if we say that self is a process, right? Not a substance, but a process. So this is a Western model. There is nothing, nothing, nothing. Then boom, birth happens. We live, we grow, we live, and then we die. And that's it for the science, current science. And we might continue if we accept the Western religion, right? So heaven or hell. In Buddhism, there is a cyclic process, right? But so life continues, there is another life, but there is this discontinuity, right? What happens during discontinuity? And Theravada Buddhism doesn't really say that much. It just basically says that these 2 points are joined, that 5 skandhas, whatever constitute your personality, just move from one body immediately in the next moment, right, to the body. But Tibetan Buddhism seems to disagree and says, okay, there are some bardo states. But basically, there is a difference between the Western and Buddhist religion. So in the science view, the matter is primary and the mind is secondary, right? So the reason I'm conscious and thinking and feeling heat, for example, or looking at the screen and feeling white or blue, right, is because of my mind, but that mind is derivative of matter, right? That's how the traditional science take it. And consciousness is created from matter. And some scientists basically says that consciousness is just imaginary. It doesn't really exist because they have no way of determining it. And they say the information is stored in your brain, and if you die, it's like turning off computer DRAM memory, right? Just disappears DRAM memory. Or you take hard disk drives and just smash it, scatter it. Hard disk drive. So all your information will basically disappear. So there is you are nothing at the beginning, and you become nothing at death. But the question is, how does the information get into birth, right? And there are identical twins who have. Many of them have different habits and phobias, right? Some of them are cheerful, they have different characteristics. And also some kids have memories of past life. So if nothing exists before birth, then how can you explain the memory from past lives? So DNA and genes cannot explain it. So the Buddhist view is that nothing transmigrates from body to body, right? There is no substance. It's a process, right? There is no substance. In early Buddhism, at the moment of death, the information, which is the stream of consciousness, the skandhas from the dying body, just instantaneously transfer to the next body, right? But we don't know what is the mechanism of this transfer. The Buddha has never clarified this. In Yogachara, tries to explain this a bit, says that there is here at the bottom, below this, there is a root consciousness, alaya vijnana, which basically stores all the seeds, right? And the fact that we're observing life and death is just an illusion, basically, like a dream, right? So everything is underneath in alaya, and everything else is basically illusion, dream. There are no bodies, right? And bodhisattvas come to life because they get born into dream to wake up other people that are in the dream, basically. Right? Whereas arhats want to leave the dream, and they think because it's all illusion, right? So they want to get rid of the dream. They don't care about the people suffering because it's all illusion, basically. So suffering is an illusion. So how to reconcile science with Buddhism? So Vasubandhu, he was, in my opinion, he was probably the world's first quantum physicist, right? I use this term a little lightly, kind of, but he came up to lots of conclusions which are similar to quantum mechanics. So he kind of indicate the Yogachara, or also known Vijnapti Matra, which is perception only, or which I don't like, Chitta Matra, mind only. I don't like this expression. That the mind is outside of the body, basically, right? This model that birth and death is just an illusion, but there is a root consciousness underneath it, which basically just carries on. So what is the brain function? So this would be opposite to the science view, right? In science view, brain gives rise to consciousness, but according to this model, it's actually opposite. There is a consciousness first, which gives rise to material things. So the brain could be just a locus, just where your personality is, where your attention is. So it's like a wave function of an electron. Electron is everywhere throughout the universe if I bring it to a standstill, right? But when I observe it, it just collapses at this particular point in time into a particular point in space, into a point basically, right? It has no dimensions. Electron has no dimensions, it's just a point, right? Collapses from being everywhere in the universe to here. So, and the observation, so the world, according to Vasubandhu, the objects or world does not exist outside of consciousness, right? So many people do not pay attention to the keyword outside of consciousness, so the consciousness and world is the same. In quantum physics, the observation is necessary for the wave function to collapse, right? They are quiet on whether it's a living being or whatever it does. So if you want to confound a typical physicist, ask him or her question, you know, what is the observation? Then most of them will be just quiet. They don't know how to explain it, right? But there are Copenhagen school, observation is necessary for the wave function to collapse, so universe splits according to multiverse school, right? And Vasubandhu also uses the term bija, which is seeds, as energy. He refers in his book many times as energy, basically, right? So if you have energy, and in physics, energy is a fundamental concept, but nobody knows how to define energy. Physicists don't know how to define energy. They know how to measure it, how to describe this in certain cases, but there is no definition of energy. Right? So this is also a possible thing to for commonality between the two, right? So they cannot be destroyed, only transformed, right? And with 8 consciousness, you have bijas, you have seeds. They cannot be destroyed, right? They are forever, but they can be transformed into something else. Another way to confound scientists is to ask, what is consciousness? There is no definition of consciousness, basically. So in 1994, David Chalmers, he studied this and he came up with the concept of qualia, or subjective experience. He said, what does it feel blue? What does it feel to have pain, for example, right? And he defined the problem of consciousness, the definition of consciousness, explanation, as the hard problem, in contradiction to easy problem, which is sending people to Mars or finding cure for cancer. So these are easy problems, right? Because we know how to send people to Mars, right? Because we just need money, right? We can calculate, we can do all the materials and everything. We have a path, we have a pathway to do. He thinks there is no pathway to understand consciousness, basically, right? So he wrote many books and he tries to get people try to understand what consciousness is. Interesting thing got developed with a von Neumann-Wigner interpretation, which were dissatisfied with this shut up and calculate motto of Copenhagen interpretation, which basically, it corrects all the equations are fine, you can build atomic bomb or build a quantum computer, you lots of explain all the experiments with this, but you don't know how to interpret this. So according to their investigation, without explaining the observer, the quantum mechanics is not complete. The consciousness has to be there, basically. And the reason was very straightforward. So if we make the matter very complicated, right, very complicated to give rise to brain, the brain creates consciousness, right, according to some physicists, at which point the consciousness happens, right? And then the consciousness starts to observing itself. So all the atoms, all the matter getting together gives rise to consciousness, which causes the wave function to collapse. But the consciousness would look at itself. So the world basically starts collapsing on its own once it becomes more and more complicated. So they say that addition of these electrons, all these atoms and energy and so on, cannot possibly give rise to consciousness. Consciousness has to be beyond that, has to be on top of that, right? So they devise certain thought experiments. For example, one of the experiments is kind of similar to Schrodinger cat, but instead of killing the cat, there is a experimentalist measuring spin of atom up and down, spin of the electron up and down, or whatever quantum measurement it is, and the experimentalists is in the enclosed box. So it is called, she's called Wigner's friend, and Wigner is outside. And there is a result of atom, let's say, splitting or measurement of spin up or spin down, right? That's a quantum measurement. And so the results is clear inside this box, but until Wigner, the scientist that came up with this, opens it and gets communicated with the scientist inside, the whole system is in the state of superposition, basically. So it's collapsed for the scientist inside, but it's in the superposition for Wigner. Very similar concept to Schrodinger cat, which hasn't been properly explained by the scientists. So the point here is that the consciousness cannot come from matter. It has to be outside of this. Otherwise, it will all start collapsing it, and basically the system would just observe itself. So one of the things to explain it, so this is my interpretation, is to basically use the delayed choice experiment. Remember this slide going from another galaxy billions of years ago, and the past does not exist. Only reality happens when you observe it. I'm using this picture I showed before with multiverses because Buddha never talks about multiple universes. So there is a pruning, basically. At certain point, depending on the karma, again, this is kind of speculation, right? This is an early explanation on what's going on. There is a decision, and because at certain point in the past, you observer, the past doesn't exist, so according to that observer, this split doesn't happen. So it might split momentarily, but then it basically doesn't go anywhere. It just gets pruned. So the whole tree gets removed, right? Over here, when I'm here, over here, this doesn't happen because according to this observer, the past did not happen, so that doesn't exist. Basically, gets pruned out. So this is the quick, so I'm not an expert in Yogachara, so Doug is, so hopefully he can help me to try to equate the findings of quantum mechanics with Yogachara. I would like to make this equalization, equate them. So according to my understanding, this is the world before we observe it. It's just a bunch of wave functions. When we observe it, we see this. But when we don't look, this exists. So in my understanding, and this is a Schrodinger equation, right? So psi is a wave function, is this, right? It goes because of these energies, bijas, right? There is energy, this Hamiltonian function. It moves, transforms strictly without any errors. So there are no errors. So the wave function is alaya vijnana, the eighth consciousness. The energy, the Hamiltonian over here, acts on this wave function and develops. And this is like evolving consciousness. We have seeds and evolving consciousness. If there is this collapse, I put it in quotes because collapse of the wave functions most likely does not exist. This gives us rupa, right, which is the form skanda, which is this. And according to this explanation von Neumann-Wigner interpretation, the consciousness is much more than the sum of the matter. So it's above it all. And that would be Tathagata Garbha, the pure consciousness, right? Not the skanda consciousness, but the conscious awareness. So Doug, do you agree?
We'll take another hour and a half, but by the time we finish, these people will all have be in some sort of samadhi, so they won't even know. This is a good start. Are you passing the? Are you are you done? Are you asking a question?
I have another 100 slides. You want?
No, let's wait. Just for context, so everybody knows, this is kind of an ongoing conversation. We're going to have phase 2 of it in another conversation where we take up this right here and kind of look at it from Yogachara Abhidharma constructs. But I think today, if you could keep going and then have some questions from people on what you've done, because I think it's raised, hopefully everybody in here has been raised many, many, many questions. And overall, we've talked before, and overall, I'll have a few comments when you finish, but I think the whole point of us having this discussion is that this place where, I mean, you think of Buddhism's been working on consciousness for 2,500 years, and starting from the position of mind and then constructing a world from mind, we've been used to having a world, and it started from monotheistic ideas in the West of God, then world, as the phenomenon which consciousness is an epiphenomena. So it seems like we have an opportunity here to bring this dualism that's, I think, made everybody's life a lot of suffering together, and I think there's lots of opportunities to bring them together by looking into what Buddhism has said for 2,500 years about consciousness and mind, as you started making suggestions here, and then showing how that long discussion opens up some possibilities of not necessarily answering questions that may remain outside the realm of the paradigm of science, but by kind of working together in the conversation can see where there's not really a contradiction at the level of lived experience. In a Yogachara terminology, we have imagined, conditioned, and real as categories of fundamental experience. And all of this realm that we're talking about here is in the conditioned realm, which we live in, is the kind of, I would put it, the isness of each moment of experience. So these explanations that have been developed in quantum physics have developed within a certain paradigm, and by you giving us an opportunity to look at it from the way that you presented them to us, they're open to dialogue that they really weren't open before if you took most of your assumptions of a kind of materialistic, deterministic kind of scientific view. The advantage that we have from Buddhism is we don't have a monotheistic, a lot of categories of monotheism that we have to apply to it. So Buddhism has open categories in terms of causation that leaves the question very, very open in terms of the dynamic of the quality of karma. I mean, when we talk about karma, we're talking about very dynamic. And when we get to something like Abhidharma, I've always translated seeds as little packets of energy, as energy packets of potentiality. And the energy packets of potentiality in coming into contact with something through the senses, which we could get into in a lot of details. It comes into contact with the senses. At contact, there's a potentiality of this energy packet that comes up to consciousness as an association with that experience. So there's this constantly dynamic quality, and our experience is just a constant dynamic quality of that moment to moment to moment. That both has a certain amount of freedom in the sense of the more still and quiet a mind is, the less the force of power of the karmic conditions are. So what we're trying to do, we're working with concepts of intentionality. When we're working in Buddhism, though, we're not talking about freedom in the way that we usually use it in a Western context, and we're certainly not talking about an agency of self. in the sense that we have, a soul that we have always have to deal with in a Western context of thinking. We just have an ongoing process of karmic conditioning that's very forceful and very powerful. And for anyone to actually be able to see in any kind of freedom from the force of that looks deterministic. And if you were to measure it from the outside and look at most people, if you just know certain categories of their experience, if they don't have any space in those categories, they actually are very deterministic in terms of their outcomes and from a karmic conditions. But we have through Yogachara this entire construct to look at that mechanism of mind and see where the areas in terms of that mechanism of mind have some potential opportunity to change the direction of those karmic conditions through certain kinds of understanding of both the nature of karmic conditions in terms of their categories, and also the possibility of developing a kind of freedom of intention and have a kind of sense of stillness. I mean, I would say that to a large degree, all of meditation and mindfulness is attempting to develop an open space in that flow of karmic conditions, and in that space, there's something happening of consciousness that it would be very interesting to look at in terms of how that open space then in turn could be talked about within a quantum level of effect. Because the division between external and internal isn't that, I mean, we have that sort of dualism in our minds, but from a Buddhist view, there isn't really that dualism between object and subject. So this opens up the conversation, and then we'll get in more detail in the mechanism of maybe the next time around and give people an opportunity to ask you some questions. I'm hoping that we can use this next half an hour to ask some questions of, since we have you here, we don't have you here very often because he's just visiting this week or so. So if people have some questions they'd like to ask, this would be an opportunity. So you want to finish though first before we take those questions?
Let's finish.
Okay, you want to discuss the questions?
Sure. Maybe people want to ask a questions. Can raise your hand and we can give you a mic. Okay. The first one.
So you went through the 2 delayed choice experiments kind of very quick. So I just want a little bit of clarification, because it seems delayed choice experiments is trying to. Okay, my understanding is, if we measure it, then it exhibits particle-like behavior, right? Whereas if we don't, then it exhibits...
No. This experiment is always measured, right? There is a detector here, there is a detector here, there is a detector here, detector here. This is the source. So it's always measured.
Right.
There is not if we measure, we do measure.
And can you explain the delayed choice experiment a little bit? Like what it's trying to do? Like what is the difference between placing a detector on the top right versus not? Yeah,
so there is a detector here, there is a detector here, right? And the light basically goes through both of them. There is a splitter, so 50% chances the photon will go through. That's statistical, right? It gets reflected 100% of the time, right? So 50% of the electrons will go here, 50% here. So we are sending one photon at a time. Right? The technology exists, no problem at all, right? One photon at a time. And we measure here, and we measure here with 50%. So they are particles. They are not waves, they are particles, right? Because wave would split here, would split here. Now, with this experiment, we also put the beam splitter here. So it means that half of the photons will go here, half of the photons will go this path, and then half of the photons basically go through, and half of the photons will go through, half of the photons get split. But the distance is in such a way that this path and this path, they are separated by pi over 2, 180 degrees. So they cancel each other, right? And the only explanation is that if the photon travels as a wave, so it's not a particle, it's a wave, basically. Here is a particle. So the question is, which stunned everybody, especially John Wheeler, how does this photon know of existence of this beam splitter? What nature to take? Right, and basically he devised this experiment where the photon is basically coming from different galaxies billions of years ago, right? So how does the photon, when the photon is going towards the Earth, how does the photon know whether to take the particle interpretation, behave as particle, or behave as a wave?
And you can see on that slide, past has no existence except as recorded in the present, and the universe does not exist out there independent of all acts of observation. I mean, that's like Buddhism 101, 101, 101, and it solves a lot of problems of idealism. The great thing about looking at it from this vantage point is it also solves a lot of problems of Buddhist misinterpretation of what Buddhism is saying. It's about this not independent of acts of observation in terms of its existence in any way in which it could be, it could be experienced. So I think a lot of the slides that were presented, we can take up and look at and begin to look at how we might bring the conversation together between a lot of these presentations today, and how Yogachara would come at them to both clarify Buddhism in the present context of what it's talking about clearly, and also from a true scientific view of what actually science can say or not say, bring consciousness and experience back into the forefront of what science is about. Because at the end of the day, science is something constructed by human experience, and within human experience, the effects of it in terms of any kind of ideology or development of the theoretical constructs comes back, obviously, onto human experience. So bringing these two together, I think, will be really helpful over time. So we've just kind of started a conversation, and it'll go on over time. So was there somebody else had a question?
On the end.
I was wondering if we could look at that last slide again, and I was wondering about the Hamiltonian variable or something, because I was wondering about the role of virtue and right action in this picture of if that could be sort of a evolving consciousness or part of that Hamiltonian operator, as far as
Well, the consciousness is above it, right? Is above it. That's what this experiment, Wigner, von Neumann-Wigner interpretation says. The consciousness is above. Consciousness cannot be part of the closed system, cannot be part of the universe. It has to be beyond it.
So what's the role of virtue in this picture as far as evolving, in terms of karmic actions and acting correctly in the world and having that have an effect on your consciousness? Because I think that's a big part of religious view that isn't always integrated into a scientific view, and I see those as a necessary place of alignment for this conversation.
Well, I mean, when you look at this equation, you cannot say this is virtuous and non-virtuous. I think bijas are neutral. They are not. They are not positive or negative. They are neutral at the core. This is what Yogachara says, right? Every seed is neutral. Our mind gives the interpretation of this.
So the seed, that these energy packets of potentiality don't carry the issue of what we're using. Virtue is wholesome or unwholesome, right? So Buddha has only one category, moral category, and that's suffering or not suffering. There is no other moral category. So you're either taking an action that is on the path towards greater amount of entanglement, greater amount of like karmic, being increasingly the pure mind being taken up by something that's entangling it. And so there's a karmic flow of that entanglement. These seeds of potentiality are the history of that entanglement. And they're not a subjective, even in Buddhism, you get to the Tathagata Garbha, they're not something that's only something subjective. The way that each of us is experiencing them is, of course, within our own frame of, because that's where we are. The focus of our concentration is on me, on mine, the narrative of this life. So all the energies right now is on that. But that's just a limitation of your mind. I mean, that's not actually what your potential of your mind is. So the question of virtue is a really good question, but we have to take virtue to meaning, okay, so what is it that leads to more entanglement or more freedom of mind, so more happiness of mind, which is just the sense of that kind of freedom and so forth, and how much more of it is actually getting tied up, limited, entangled, because the main thing that the Buddha is concerned about is constantly looking at what you get attached to and discrimination. There's two basic problems that he's pointing out all the time, and that's getting attached, which then limits the freedom of the possibilities of what's arising. And discrimination, which he means by discrimination, already having a prejudiced view towards what it is that you're experiencing in contact in the senses that limits the possibility of you actually seeing things as they really are. So these limitations that come about are the moral ground of suffering, which is the moral ground of unwholesome activities and thoughts. Wholesome thoughts, so you say, well, then what does that have to do with something like loving kindness? Or what does that have to do with something like generosity? Well, try generosity as a mindset over resentment and see what happens, okay? I mean, just try as a, so if we take a Buddhist approach to this, we would say try generosity and gratitude rather than resentment, and see what happens to the mind in terms of experience that opens up or closes down the heart and the mind and the process of this that then we could talk about. So what universe would I see through resentment? I'm going to see I'm going to have a different universe that I construct out of, all you have to do is look at politics, right? Modern politics. Okay, what universe do you create out of resentment in terms of the form that you construct it to be, and what do you form out of generosity? So when we talk about moral virtue, I just want to make sure we're talking that kind of language. There's a lot more to say about it, but we're talking that kind of language. So there's everything, there's all kinds of virtue here in the form that you would actually see, but it's not Western. It's not a Western idea of morality, of some judging God or some, it's the actual mechanism itself. It's the dynamic of the mechanism of the flow of your experience. And you're completely responsible at some point for it, because we get into this intention moment by moment, the actual directionality that you've actually created over time that gives those packets their energetic field of possibility are all been created at one level or another from your own personal experience. And there's not another realm outside that is ultimately responsible for what it is that you experience within that construct. And we can get into lots of that. But it's, even if we get into a question like virtue here, you can see how that would overlay this quite well. And the form that we see here, we see form, feeling. You can see we're talking about here. Here's our mind before form. When the eyes see something through form, and it constructs a world, it constructs it from the wave function of the form is an act of consciousness, an act of and how does that form of consciousness form what world that we actually perceive? It's through all these elements of experience that we've had, conditions that we've created in the past that then through the eyes, ears, nose, seeing things, we actually construct what we see in the experience of that through the interpretation of that and then the meaning of that we actually have. So Yogachara gives us a very elaborate way to observe the mechanism of that process. This is a perfect kind of equation that we could work with, and we could spend a lot of time looking at all the different elements and angles of this diagram up here. So
we have a question from online. Bernadette asks, as a complete non-scientist who read Carlo Rovelli's book on time with interest, I thought Rovelli was suggesting complete randomness of change. Professor Bogdan said everything is deterministic. So she was asking about this determinism.
Yeah, in the wave function, the evolution of this wave function is fully deterministic. There is no chance. There is no randomness. The problem is that we cannot observe psi. We can only measure. So during the measurement process, we have to somehow collapse it or go through otherworld interpretation. But psi is just evolving without any randomness. You put energy into this, Hamiltonian, that's the energy, and it evolves exactly as the equation says, basically, right? Otherwise, if there is randomness, atoms wouldn't exist. Atoms would just disappear, right? Molecules would not exist. Molecules would disappear if you had any even a tiny bit of randomness. There is no randomness here.
So can I ask as a follow-up for that one is, so how do you see free will in quantum mechanics? Or there's no free will?
So you need to bring observation here, right? And if you observe this, then something happens, right? Either wave function collapses, or there is a split into different superposition of different universes, basically, right? So we go back to the Everett's interpretation, or basically split of the universe, and that's free. That's free will, right? You make a decision, and you live in that world, basically. You split into that world, and that world is the result of your decision.
there's no free will in Buddhism, though. I mean, if we're talking about Buddhism, in the way that you're talking about it in a Western context of free will, there's no agent that would have free will. The question is you're a set of karmic conditions that you've already set into motion. And if you look at your day, you're mostly deterministic. To find a moment that you're not in a deterministic mode of your own construction would be very difficult. I would challenge you to sit. You're going to have to sit a lot. I would suggest you better be on the cushion quite a bit and opening up quite a bit of space before you can actually see in the process of the karmic flow what isn't conditioned.
No, Doug, but if I drive, if somebody cuts me, I can either show the finger or I can be quiet, right? So there is a free will in that.
But the degree to which you're quiet has been conditioned by your multitude of cultivations of that quietude. And the reaction to heading them off, pulling out a gun and shooting them is also based on a whole lot of conditionality. So there is choice at every moment.
But sometimes I feel both, right?
And sometimes you feel both. Sometimes you're ready to be, both. But you can see this question is a really good question for us to spend more time on, because the idea that people have free will right now is pretty much an illusion. Is there a potential for something like free will that we could actually look at? There is. At the place of intention, with this intention in the 5 universals in Yogachara, where you're starting from attention, contact, feeling, thought, and then you have intention that moves something. So intention moves something, the activity's gone. So something moves. But that movement of something, you have to look at Buddha, the whole aspect of meditation and mindfulness is developing the 6 consciousness, the 6 consciousness of the cognitive active consciousness, to calm that down and still that down so it has some space to observe in.
Yeah, Doug, but if there is no free will, then the universe will not split, and we'll be living in a very boring universe which doesn't split.
It will. But the question of it's not that there isn't a potential of free will, but it is, when we talk about free will, the characteristics of mind that it takes to actually observe an action of free will has very skillful means in Buddhist terms. There's a tremendous amount of skillful means that have to be, there is a potential for a different choice at every moment of experience. But in that seeming choice, there are incredible forces of karmic conditioning that are engaged in that moment of in. So the degree to which there actually is a space that we would call free will in this kind of way requires the development of the mind in a way that actually can see what's going on at a much slower pace than most people's minds operate at. And what you're doing with meditation and mindfulness is you're slowing down the process of the karmic conditions. At the first level, before anything else is going on, you're slowing down the process of the karmic conditions enough to actually begin to pick them out. And then if you can pick them out, the Buddha gives you all kinds of information about which has which characteristics. And if you pay attention to this one, it will create these kind of problems. If you pay, Abhidharma is just categories. It's learning. The reason Abhidharma is so difficult is it's giving you an entire analysis of the mind in almost every category of thought, and the outcome that will come from actually paying attention to that thought. It's a set of categories. The reason that we still don't use Abhidharma is you're going to need 5 years in a monastery to learn the categories to apply to the mind, and then you're going to need 5 or 10 years in the monastery to put them into effect to make the changes that Abhidharma wants you to make. And that seemed a little bit impractical to the average person at that, okay, we're not going to be able to quite go to this level of refinement of the mind. So the question is how we develop the mind that each of us have to use it in a different way than we're currently using it. And there is something like akin to free will, but it lies pretty far down a road of development of awareness to actually be able to use it. And what most people are using is not that. Most people currently think that acting on impulse is freedom, that's exactly the opposite. So the reason that everyone is currently having a bit of problems is freedom is not acting on impulse. The impulse itself is already incredibly conditioned on all kind of different levels. So that's why you have to start by getting some kind of control over this mechanism of mind so that this possibility that we're talking about of free will, in other words, going in a different direction than the karmic conditions that you've already set into motion are going to carry you. And then we can actually talk about, and then what's really interesting is we could actually begin to even talk about bodhisattvas, Tathagata, Buddha. When we move into this realm, when we're moving over into your realm, we're almost moving into the realm of the level of the Tathagata realm, where it's actually interpenetration of all sentience between. But again, those realms that we're talking about in Buddhism later on, Avatamsaka realms, Lotus realm, all these other realms of talk, discussion, they're realms that open up to us in being able to see only after we've opened up the space where the doorway's been open for the mind and not be in the current conditional karmic conditions that you're already so caught up in that you're not going to be able to see the space in which that's actually occurring. So anyway, that's just an aside. But we'll spend more. I think that if we look at this, we have pure conscious awareness, Tathagata, which we're talking about in something like, especially the Avatamsaka, we're talking about in Yogachara at a certain level of realization. This Tathagata only opens up, and it would suggest, that Yogachara would suggest, that if you actually got past the karmic conditions that you currently constructed that are entangling your mind so it doesn't have the freedom to actually experience, it would actually see that it's actually interpenetrating the all sentience in the whole, on all the universes of time and space, directly. I mean, your actual mind would actually be but you can't see that. Why? Only one reason you can't see that, and that is your attachment to your own trip, right? Which you're very attached to, and you're spending all your time thinking about, and that's just a construction. It's not real. It's just something that's been constructed. So when we move to to using it across here, you can see we can this world that we're looking at here, the collapse of wave function. There's incredible possibilities on this other side of this.
Yeah, and another surprising thing is that this pure conscious awareness is just one for everything, for the whole universe. There is no pure conscious awareness, your pure conscious awareness.
And
it's just there is only one.
And there's only one, and it interpenetrates the whole universe. The Sakadagarbha is the womb, the mind womb, right? So anyway, we have a lot of future conversations. Any other questions?
So given the
before-
time, maybe the last question is someone want to ask? Cuckoo Jews. Okay, let's do this part.
He'll always create trouble. You can always count on him.
I'm intrigued by the idea of entanglement in quantum mechanics, quantum computing, and using that individual electron entanglement in a powerful way to solve very complex problems. And it seems that there is a Buddhist corollary there. If you look at the entanglement, often is considered to be problematic if you get too entangled with what's going on. But at the same time, the Bodhisattva resolve comes, the Buddha comes back and consciously involves in reality, what is going on, in order to solve the problems of the human condition. Could you talk about that concept from, I don't know really what my question is, but just, can you talk about that idea of using entanglement as a means of solving problems in the human condition?
Well, so entanglement has been shown at the photon level, at the electron level, atom level, and also molecules level. So as years pass by, scientists entangle more and more things, high complexity structures. So basically, when I put two electrons, these electrons have the same property. They cannot be divided. It's like one particle. It's not exactly, but it's just like one particle. They are indivisible, basically, as far as the properties are concerned. And in order to have this communication with other electrons, they have to be entangled, for example. Quantum communication have to be. We have a European project which basically connects the two quantum cores, two quantum computers, through entanglement. So we are sending a photon that is entangled with qubits on one side, and they go to the other side, and they carries the entanglement. So this is the only way to carry this communication. So I guess if you want to bring it to a higher level, right? I mean, molecule is what scientists are able to do, but you are talking about more than just molecules, right? You're just human body. Can you entangle human body? Well, it's difficult to say scientifically, but according to physics, entanglement is the only way you can quantum-wise communicate the information. So if a Buddha wants to entangle, or Bodhisattva rather than Buddha, wants to entangle with connect with human beings, there has to be entanglement, in my opinion. How it is done, you know, they are much better scientists than we do. We are at the atomic level yet. They are probably entangled at the much higher level. We don't know. Doug, do you know?
Yeah, well, I mean, Again, I think we're going to have to open up the gateway. You have to open up the gateway of the mind, of experience. And when you open that gateway up and it's not so conditioned by your current, limitations of conditionality, I think what's been reported over and over again and what's been experienced is that sense that I am experiencing something in my process that's something different than your process is just something I'm making up in separating myself. So one of the delusions of self is that separation. So there's, from a view of a bodhisattva and a Buddha, the entanglement is a given. It isn't that we're not, it's that somehow we try to create a delusion of disentanglement.
Well, during the process of Big Bang, right, everything was just collapse, the whole matter on the universe in one place, and there was a Big Bang. So I would say that the stars on this side of our sky and on this side, they only got in contact initially during the Big Bang, and since then there's never been a contact, basically. So they have to be entangled, in my opinion. So I think Doug is right, saying that there is more entanglement than disentanglement, depending which interpretation you take. In the many-world interpretation, everything is basically entangled. There is no disentanglement. Disentanglement is just an illusion.
Aren't you suffering enough from it already? Have you suffered enough from your disentanglement? And again, going back to suffering, going back to what the Buddha is, he's basically saying we suffer from the illusion of self, meaning disentanglement, in an artificial way, and then we feel separate, alone, and we're not in generosity, we're not in patience, we're not in loving kindness. I mean, what are the major categories of a bodhisattva and a Buddha? It's loving kindness, constant compassion, which compassion just means entangled. Compassion is engaging in others' sentience as they're experiencing themselves without the projection and interpretation of them that's taken from the self in the way of directly experiencing them in their process. So you directly feel the feelings of others when you're a bodhisattva rather than being only attached to your own. Now, those other feelings of others were always there, but because you were only paying attention to yours, you got disconnected, okay? And then as you go through the different, the different realms of this, you can see then we have sympathetic joy, the third primary, attitude of a bodhisattva, a Buddhist sympathetic joy, which is being really, really happy for the joy of everyone else, which you usually aren't, because if they have more joy than you, then you're like really upset about their joy. And then equanimity as the fourth element, which is this constant ability to stay completely aware of what's going on without pulling yourself out of that all the time, with the history of your disentanglement in the conversation we're having right now, into a separate entity that's somehow creating itself in its own karmic conditions and identifying with that as the entire realm of your experience, which then leads to the kind of, current narcissism. I mean, everyone's basically at this point a kind of narcissist, because the place of reference from even early childhood in the process of this is, we're constantly only seeing what it is that, and it's almost been deified, this looking after ourselves, fiercely looking that we're not being mistreated in some kind of way, fiercely looking at holding on to the space of that is a kind of suffering that everybody is having. But the natural space is this, it's not finding an unnatural space and finding this entanglement. That's just the natural condition. So we could go on and on with that, but we're going to stop because 2 hours is probably, most of you guys, people would probably like to go on and do something else, although, we can go on. The two of us can go on forever, so don't, he's been going all day. I've been going all day. But you folks probably want to take a break.
It's a good warm-up.
Yeah, we're warming up, yeah.
Disentangle from us. So we really appreciate Professor Bogdan and Professor Doug's kind of presentation tonight. And we wanted to maybe just share a few announcements about what's coming up. I think the first one.
Sure. So if you are very interested to investigate more about how the Buddhists present the mind in the Yogachara school, Professor Doug Powers holding a course, online course. You can also in person join, but it's in Ukiah, Dharma Buddhist University, 6 p.m. every Wednesday. So if you wish to be part or have more information, please leave your contact on the list. So 6 p.m. Wednesday, Yogachara, mind only, or consciousness only, school.
Perception only.
Perception only. By Doug Powers.
And if you're interested, we're also having a meditation here at Berkeley Buddhist Monastery on March 2nd and the 9th, kind of a meditation day-long. We're going to theme a little bit around Yogachara. You can maybe think about it as disentangling ourselves from ourselves to be entangled with the actual interconnected web of the universe, using a certain kind of language here. But really looking at what Doug was saying about these categories or places to look in our experience that actually disentangle us from our story to actually open up space, to be able to actually choose a kind of place where we actually have less suffering or less kind of collapsing of our awareness in these kind of particular places of anxiety, fear, so on and so forth. So if you're interested, you'll see there's a poster out in the front. We'll start at 9 a.m. and go to about 3:15 p.m. People can also join us for lunch. There's a place you register, so we just know the number of people coming.
So it will be a mind lab. You can look at in your heart, in your mind, and ask yourself how much I have a space of free will, or I'm deterministic moment by moment. And we can expand that spaciousness, hopefully. We present some basic concept of Yogachara and try to learn together how we can apply them in our everyday lives and in meditation.
I think the other one is on April 7th. Do you know what time that is?
April 7 is 10 a.m. California time will be 6 p.m. in Dublin. It will be online continuation of this dialogue with some emphasis of the Buddhist teaching, but still we'll keep in mind and hand the quantum mechanics. And basically, Professor Doug Powers, Professor Bogdan Staszewski will continue.
We'll just sort of carry on and take a look at these and see what, come at it a little bit from Yogachara, but then also come back to these suggestions for where the discussion could begin to happen.
And I know we didn't get to everyone's questions, so if you have any you want to write down on the pieces of paper back there and leave it with us, that can be passed to Bogdan and Doug, and they can kind of think about it and see maybe that can address those in the upcoming talks.
And if you wish to enter another universe, March 25th at the City of 10,000 Buddhas, we have a retreat. We recite the Guan in Bodhisattva's name for 7 days. And Doug Powers will also have a series of classes introduce this practice. It will be 7 days in-person retreat in Ukiah. We can find more information on our website, berkeleymonastery.org, and Dharma Buddhist University website, drbu.edu.
drbu.edu. So yeah, if you want to enter another universe, that's definitely another universe.
Multiverses.
Yeah, there's multiverses there for sure. Everyone has their own reality. And you really get to see it. Anything else we're leaving out?
Do you want?
I don't want to say anything to kind of concluding words.
So how we can live with this, knowing this is
Now
paradox.
that I know that the reality doesn't exist except like in this present moment, and I just constructed everything right now, every moment.
And how to swallow the paradox the cat is alive and dead at the same time.
Yeah, that's a good question. Maybe we can answer that next time.
Well, I think you left us with that you feel like the work he's doing with quantum computing is actually working from a multi-universe perspective. Did everybody I hope they got that in that conversation, which is, I think, something to go away with. The current cutting edge of actual mechanical work in terms of the edge of developing technology in his mind is the reason that it's working is a multi-universe theoretical construct of what's happening. So if you could just see yourself as a series of events in new universes all the time, that might open up something for the rest of the evening to explain a lot of what's going on. Okay, thank you very much.
Thank you.
Appreciate everyone being here.
Thank you.
Now that was, is that going to be, is it available? Did you make a tape of it?
Yeah, we streamed that online.
Okay, but I mean, you made it, you streamed it and kept it.
It is recorded.
Yeah, because the people here, there's a lot. There was a huge amount there to work on. So maybe you can make it available to people if they want to ask for it. So
If you have your emails or something, want to maybe leave it with us, we can send
I would think you need to see that a couple of times. Thank you very much. That was great.
Yeah.
Yeah, yeah. Kind of a question for you. What's that?